So our next presentation is by a familiar face, a founding member of NCLOG and a regular event contributor. And as discussed in my introduction, the driving force of the RBKC Lead Modelling tool, and one of the most proactive CLOs you'll encounter, Robert Tyler, Senior Contaminated Land Officer at the RBKC. Robert has dealt with contaminated land and local government for 25 years, with over 15 years spent working in London. Apart from the full range of Part 2A and planning work, career highlights have included working on the 2012 Olympics, and more recently being involved in the Grenfell environmental check process and serving communities work for. Robert is on the steering group for the West and East London Land Contamination Officers Group, attends the National Brownfield Forum, and has previously served as a committee member on the Geological Society Land Contamination Group and the National Contaminated Land Officers Group. Robert's presentation is titled Dealing with Lead Through Part 2A, RBKC Lead Grenfell Investigation. So I'll pass over to you, Robert.
Thanks, Anthony, and thank you for those kind words. That's very nice of you. Yeah, I'm here today to kind of present kind of a Part 2A case study involving lead. And it's a project that I dealt with back in 2001, 2002. And Anthony said it was kind of part of the kind of Grenfell environmental checks, but in fact it wasn't part of the main project. It was kind of a follow-on case study, and kind of the work was kind of undertaken by AECOM, and in particular David Dyson. In terms of consultants, I've dealt with quite a few projects over the years, and I think I can't highlight enough about the importance of having a kind of a good consultant and kind of one that you can work with in partnership. Because at the end of the day, as local authority officers, we need to input into the reports and make sure that we can kind of make the decisions under Part 2A at the end of the process. Yeah, so it was a kind of a relatively kind of large public open space, a managed area, kind of 10 ground floor apartments. As you can see on the right there, I mean, it's quite a nice kind of landscaped area. The kind of the apartments on the southern part of the site, there were kind of 6 adult single occupation units, and then on the kind of the west side there were 4 kind of 2 or 3 bedroom kind of family units. The adult kind of apartments, adult only apartments, had direct access onto the area of open space. The kind of the family units, they had kind of ground level balconies almost, so there wasn't direct access, and it was relatively high, so you'd have to be a bit older and be able to kind of jump over them to get to use the area. But there was direct evidence that people were using the open space, and it was quite clear that they were tending to treat the area kind of outside their property as their bit of garden. So we developed a conceptual model. I mean, we weren't just dealing with lead at this site. There were kind of other metals and kind of organic compounds, and also kind of ground gas. But I mean, in this particular presentation, I'll just deal with lead, which was the key issue at the site. In terms of the work undertaken, I mean, I think we were very clear with AECOM that we wanted a high level of investigation work, and so there were about 90 hand dug trial pits across the area. So that was about kind of 5 to 10 per kind of property, and kind of just over 190 soil samples, of which kind of most of those were kind of for lead. I mean, if you see the table at the bottom there, you can see that most of the sampling was undertaken at ground level and 0.1 to 0.2 meters, where kind of people had most access, and kind of relatively wide sampling was carried out at greater depths as well. And as you can see, I mean, the topsoil was really nice topsoil, kind of as you'd expect in an urban area, few inclusions of brick, concrete, and maybe a bit of ash, but no, nothing too suspicious really. I should have said earlier that I mean the reason the site came to our attention is that we, as part of the Grenfell environmental checks process, 4 ground level samples were taken, and the concentrations were kind of between about I think it was 900 and over 2,000. So it kind of definitely got our attention, and we felt that there was a need for further investigation. Yeah, so it was a kind of a relatively kind of large public open space, a managed area, kind of 10 ground floor apartments. As you can see on the right there, I mean, it's quite a nice kind of landscaped area. The kind of the apartments on the southern part of the site, there were kind of 6 adult single occupation units, and then on the kind of the west side there were 4 kind of 2 or 3 bedroom kind of family units. The adult kind of apartments, adult only apartments, had direct access onto the area of open space. The kind of the family units, they had kind of ground level balconies almost, so there wasn't direct access, and it was relatively high, so you'd have to be a bit older and be able to kind of jump over them to get to use the area. But there was direct evidence that people were using the open space, and it was quite clear that they were tending to treat the area kind of outside their property as their bit of garden. So, I mean, ACOM kind of produced some very nice kind of plans identifying concentrations found across the site. I can't actually see the concentrations to kind of read them off, but I mean, you'll see that this is the ground level sampling, and you'll see that there's a large number of kind of orange coloured locations, and those are kind of just over represent concentrations in the soil of just over 1,000 to just over 2,000, so kind of quite elevated at ground level. Yeah, so as you can see here, this is the 0.1 to 0.2 meters where we found kind of the high concentrations of lead. So apart from the orange locations that you saw a lot of at ground level, there were also quite a few red locations here. The lighter red ones were kind of over 2,000 to 4,500, and the deeper red kind of over 4,500. So really quite high concentrations in the soil. Next slide. So I mentioned that we did some kind of deeper sampling as well. So this is kind of 0.3 to 0.4 meters. So fewer samples, but I mean, the general gist is it's more like kind of the surface level sampling. So still quite relatively kind of high, but much lower than the 0.1 to 0.2 meters. Next slide. So we got some box and whisker plots, and the main ones to look at are the kind of the orange box, which is the London Earth data, and then for the site you've got the grey box, which represents all of the data, the yellow box, which is ground level samples, the purpley blue box, which is 0.1 to 0.2 meters, and then the kind of the blue and kind of orange at the end were kind of deeper samples. So I mean, you can see quite clearly that it's kind of quite elevated above what you'd normally expect in London. You can also see that the distributions of the samples are generally log normal or fat-tailed. So kind of overall, the median and geometric mean statistics were used to compare to criteria. Next slide. So this is just a summary of data. And yeah, as you can see, I mean, the highest concentration we had was kind of over 38,000, which is pretty high. There are a lot of exceedances of around kind of 5, 6, 7,000. And I mean, when you compared the data to kind of available criteria, so including, for example, the category 4 screening level for residential without homegrown produce, and also category 4 and category 3 type criteria generated as part of the Grenfell environmental checks process, you can see that kind of most of the samples kind of exceeded those criteria. So it was clear that we needed to do some further DQRA. You can also see I've included a table of the bioaccessibility testing that was undertaken. And it was actually found that kind of overall from 9 samples, the average was 68%. And so that was kind of what was used in the kind of the risk assessment. Next slide. So the first step was to kind of calculate a step 1 site-specific acceptability criteria, or a kind of a category 4 type criteria. And the criteria generated was for an adult receptor, 2,100 and I can't quite read the last bit. And for a child receptor, it was just over 1,000. So in terms of the adult receptor, it was just using the kind of the CLEAR model for an adult lifetime exposure, and a soil ingestion rate, I believe, of 50 milligrams per day. And that gave the kind of the 2,150. For the child receptor, so we kind of amended the category 4 without homegrown produce screening level. So that was amended to provide the site-specific bioaccessibility of 68%. A soil ingestion rate of 60 milligrams per day was selected, and that kind of was based on the US EPA exposure factors handbook, the current version of it, for a child between 6 and 12 years. And the reason that was chosen was because there was this kind of barrier which really prevented smaller children from getting kind of easy, regular access. And there was also kind of alternative areas to play at the front of the property and nearby. So it was considered that children wouldn't always be playing on the plot of land behind the property. In terms of the exposure frequency, for similar reasons, that was kind of reduced quite significantly to 111 days. There's a table on the next slide which kind of explains that a bit kind of more clearly. And because of the way CLEAR works, you can't just kind of plug in exposure frequency, in this case for outdoors. So a time-weighted average soil ingestion rate was calculated, and that was kind of 39 milligrams per day. So that kind of produced this kind of 1,050. Next slide. So this is the kind of the table, which just summarizes how the outdoor exposure frequency was calculated. And basically, it was assumed that children wouldn't use the area during the winter period, that they would use it every day during holidays, which is kind of around 70 days, and twice a week during kind of non-holiday days. So that added up to 111 days per year. It was actually unexpectedly tested because a resident unexpectedly moved into one of the properties with children. And we actually kind of interviewed them and questioned them on kind of the use of the surrounding open spaces, and our kind of assumptions kind of stood up very well. Next slide. So kind of comparing the median and geometric means to the calculated step 1 or category 4 type criteria. Basically, with a few exceptions, pretty much there were exceedances in every case, including of the arithmetic mean. Next slide, please. In terms of adults, ground level samples kind of didn't exceed the criteria. Between 0.1 and 0.2, there were a number of the plots where there were exceedances, but on average for ground level and samples from 0.1 to 0.2 meters, there weren't kind of exceedances overall. So on that basis, it was decided that adult exposure kind of wasn't significant in this case. But obviously, there were significant exceedances for children, so we went on to step 2 of DQRA. Next slide, please. And I mean, really, the step 2, or it's more of a category 3 type screening criteria or level, was generated, and it was just over 4,500, which is kind of quite high. And the step 2 criteria, it was kind of building on the step 1 work. And so the soil ingestion rate, the kind of the changes that were made, the soil ingestion rate was kind of reduced further, and that was kind of as an average of the kind of 6 to 12 years and 12 years to adult. And again, that was, I mean, it was, I suppose, pushing the model as far as you could to get a kind of a real category 3 type criteria, I suppose. In terms of the exposure frequency of 111 days, that was also applied to indoor exposure, just on the basis that if you don't use a kind of a space, you're kind of not going to be tracking mud back into a property, so you'll have kind of reduced lead in dust. The tox value was kind of also kind of increased to the equivalent of 5 micrograms per deciliter, which is obviously the UK HSA intervention value recommendation. And again, using the kind of calculating a time-weighted average for the soil ingestion rate, the ultimate soil ingestion rate used was 13.5 milligrams per day. And I think it's really important to highlight that you shouldn't be using that for planning. That's very much kind of a worst case for Part 2A. Next slide, please. So, and with one exception, there weren't kind of any exceedances of the 4,500 level. In the case where there was an exceedance, similar to the kind of adult cases, there was no exceedance at ground level. There was an exceedance between 0.1 and 0.2, but on average, there wasn't an exceedance. So I'm not on that basis. Yeah, the statistics didn't kind of exceed the criteria. Next slide. So kind of in conclusion, as you probably guessed from the presentation, for kind of adults and people visiting the site, it was concluded that the land was category 4, so low risk. For children living at the site was considered category 3, so a kind of a not low risk. And of course, because of that category 3 designation, the recommendation was that the landowner, which in this case was kind of RBKC, considered undertaking kind of work to reduce risk levels to low. So, and that's a decision that was made, and kind of remediation of the site should be happening relatively soon. It's also worth pointing out that it was very clear that the source of the lead in soil. It was from imported soils, so it wasn't to do with the kind of Grenfell tragedy. It's also worth noting that we, just from a quality control point of view, we kind of included a suitably qualified person and got a declaration for the kind of adequacy of the work and the document. And kind of in line with the Part 2A guidance, we also produced a written statement just explaining what we'd done and the conclusions. And that's, I mean, all of this information is kind of publicly available on the environmental health webpage of the RBKC website. Next slide.
Apologies, Robert, you're at time, but also got a few technical difficulties, so you're welcome to a few more minutes. So
that's all I need. Yeah, thank you. So in terms of the remediation, without going into too much detail, in this case, kind of a cover system of 400 mil was recommended with a geotextile. Next slide, please. There were, as you probably noticed from some of the photos, some quite nice mature trees, which we wanted to preserve. And so I did ask AECOM to do some kind of averaging work, looking at different scenarios, so different depths of soil over the root protection zones and how that would kind of play out in terms of averaging. So as you can see, the situation where nothing was done, we still had some quite high averages at some of the plots. And so kind of as a result, next slide, please. It was decided that in the root protection areas, wherever possible, we would achieve a kind of 0.2 meters or 200 mil cover system. Next slide, please. Of course, I had to get in our kind of RBKC, KC 4Ls and 3Ls somewhere. But I just thought it'd be, because a lot of the risk assessment hinged on the balcony areas. And I mean, the council subsequently decided to kind of refurbish the block and to actually get rid of those to give full access to those kind of 4 flats where families might live. And so, I mean, if you kind of rewind and look at kind of what might have happened, I mean, I think with the levels, if it had been a standard kind of residential without homegrown produce situation, I mean, our standard category 3 level is 928 for without homegrown produce. So it would be a very clear kind of Part 2A site. Next slide, please. And I've done kind of a bit of modelling with the RBKC lead model. And I mean, again, if you look on the right-hand side, I've inputted the kind of bioaccessibility and also the kind of the indoor element of the exposure frequency. And I mean, you can see that, I mean, I think it's, I can't read it, but I think it's about 1200. So again, I mean, it's likely that the site would have been determined as contaminated land if it hadn't been for those balconies. Next slide. And that's me done. Thank you.
Thanks, that was excellent, Robert. And yeah, thanks again for your assistance there, Phil. Okay, moving on. So our next presentation is by Alan Yendell from the Scottish Environment Protection Agency, SEPA. And unless I'm corrected, this is the first presentation NCLOG has had from SEPA, so hopefully the first of many. And we've got your email and we've got your number now, so there's no escape. Special thanks to Alan for agreeing to present to us at short notice. He was just so enthusiastic when we spoke about joining us here today and hardly took any persuasion, or no persuasion at all. So thank you, Alan. Alan is a contaminated land specialist at SEPA and has 21 years experience working in the industry. Starting out with a small consultancy in Glasgow, he gained varied experience from work on numerous brownfield sites in Scotland, undertaking site investigation, risk assessment and remediation. After a short stint in the wind farm development industry, he moved to BAE Systems in the in-house geoenvironmental team at the former munitions factory at Bishopton, specialising in the water environment, risk assessment and managing remediation works. Since joining SEPA in 2014, on top of the day job, as many of us have other things on the day job, he's become heavily involved in supporting delivery of the River Basin Management Plan objectives to understand sources of pollution from historic metal mines and opening up funding opportunities and developing partnerships to deliver remediation work, reduce the scale of pollution from abandoned metal mines and improve water body classification. Alan's presentation is titled Reducing Lead Pollution in the Wanlock Water. So, Alan, over to you.
Thank you very much, Anthony. Good morning, everyone, and thanks for the introduction there. So I'm going to do a brief run through of work that we've been doing at SEPA in Wanlock Head, which is a very small village. Get these slides to move on. Here we go. Very small village in the southern uplands of Scotland, in the vicinity of this red star here. It's neighboured by a village called Lead Hills, and the two villages are well known for their lead mining history. Lead mining's occurred in the area from way back when, 13th century. Different metals have been mined, gold, silver, zinc, but predominantly lead. Lead is the most predominant mineral in the area, and as you can see from the map on the right hand side there, there's numerous mineral veins in the area, and these have been heavily exploited, mainly from about the 1600s, and then mining continued along with processing and smelting in the area till around about the 1950s. So as you can imagine, there's a pretty large legacy of pollution there. Now, I'm going to focus purely on water environment here. No doubt there will be potential questions on the human health side of things, but predominantly water environment today. So what are the impacts on the water environment? The lead EQS is 1.2 milligrams per litre now, as set out in the standards directions from 2024. And there's a bit of a bioavailability assessment allowed from that for DOC concentrations. We see significant pollution from the historic metal mines at Wanlock Head, more so than anywhere else in Scotland that we're aware of at the moment. Although interestingly, the most or the biggest impact in terms of distance and rivers impact is from cadmium rather than lead. So what you can see here is you've got the village of Wanlock Head. The Wanlock water itself fails for lead, cadmium and zinc, and also has a fish downgrade, which I'll talk a bit about later. The Croic water, which the Wanlock flows into, fails for cadmium and zinc. Lead levels are quite high there though, and that may change as time goes on. And then the River Nith itself, which is the main water body, the main catchment in the southwest of Scotland, flowing down to the Solway Firth, is impacted by cadmium alone, and that fluctuates on the levels. But that's enough about cadmium zinc. We'll stick to lead mainly. So I got involved about 10 years ago, nearly now. We are aware that there could be a Part 2A designation for certain sites in the area or even a wider area from a water environment perspective. But as we know, there's a prohibition or a restriction on serving a remediation notice due to historic mining impacting a water body, and that encompasses the mine itself and all the associated parts of the mine. So the smelting mill and the processing areas are also considered part of the mine. So a decision before my time at SEPA was made to focus on or to utilise the River Basin Management Plan process to try and progress things in the area. It's been a bit slow. It's been impacted by funding restrictions, but since 2020, we've had Dumfries and Galloway on board as a partner to help us deliver on that, and obviously councils have certain roles in terms of implementing River Basin Management Plan improvements. We've also developed and this is critical for the work that we've been doing, a really good working relationship with the landowner, who's a large landowner. It's Buccleuch Estates, one of the largest landowners in Scotland, and also with the local mining museum. And I'd encourage anyone that's interested in going down a mine to pop into the mining museum in Wanlock Head in the summer. Their mine tour is quite an eye-opening experience. So yeah, I mentioned funding, but we've gathered little bits of funding over the years from Scottish Government and from SEPA, and a lot of support in kind from the council as well. And the work that we've been doing has really been underpinned by knowledge sharing, particularly from NRW. And I know Louise is going to speak later on their work, but their conferences that they organise have been really helpful in terms of helping us progress from a step behind the EA and NRW. And I'll talk about it more a bit later, but we recently established a partnership project which has now got a decent amount of funding from one of SEPA's river restoration schemes under the name of the Wanlock Water Restoration Plan, and it's aiming to deliver multiple benefits as well as improving the water quality. So what are the issues? About 8 years ago, the Coal Authority, sorry, probably more than 10 years ago now, but about 8 years ago, we tried to pull some of the work in-house, and we'd had a piece of work done by the Coal Authority to understand the sources of pollution, and they did a year's worth of sampling at various locations. It did highlight the need for more sampling work, and one of the things that we did was to pull together I've called this a standard CSM, and this is just the sources part of it. But as you can see, there's numerous sources. There's at least 27 sources listed there. Now, some of those are general land-based sources where we have no definition of them as well. So there's potentially many more than that. Many of them, though, as you can see from the type on the right, are mine waters and runoffs and just surface water runoff issues. So lots of different pathways and pollutant linkages going on there. But with all that work being done, there was really a need to understand what are the most significant sources and how do we identify those so that we can target them. So we took the CSM a step further. This is an indicative catchment CSM for the area. Typically, as from a water environment perspective, we can only sample what we see, but how do we know that we're capturing all the sources? We've got various different potential sources, uncertainty, lots of uncertainty around the pathways to the river, lots of uncertainty as to whether those sources are actually impacting the river. And this is where we started to lean on, and we gained support from Liverpool John Moores University, who I met at the NRW conference. And there's a chap called Patrick Byrne at Liverpool John Moores Uni who was doing work with NRW to carry out detailed source apportionment work. Just to go into a bit more detail about some of those pathways. The stream is permeable, and I think that's something that could be easily misunderstood. And the water flows in and out of riverbeds, and in the riverbeds itself, and you can't always see that water flow. That flow is known as hyperhaic flow. But most of the methodologies that we would typically use can't necessarily measure that. Now, if you know about the problem, that's not necessarily a big issue, but if you don't know about the problem, you can really miss pollution sources. So on the chart on the bottom right here, you can see a discharge, and this is just flow measurement, measured by a flow meter, and then discharge measured by tracer dilution. And this is the technique that Patrick Byrne was utilizing. And you can see there's a significant difference in the two flows that are measured there. And what you're seeing here is that this tracer dilution is picking up this hyperhaic flow. And this was a technique that was first used by the US Geological Society And essentially what we're doing is we are, just pop onto the next slide, we're injecting a tracer at the top end of the study area, and we're injecting that for quite a long period of time, a week, 2 weeks, and that tracer is usually a salt tracer, but a stable one, so in this case bromide salts. And what you can see from the graph on the right here is that over time, as we inject that tracer, it stabilizes, and you get a stable trend. And what you're seeing there is that the tracer has infiltrated the entire river flow, included in the hyperhalic zone. And that then allows us to collect samples all the way down the river course, and analyze for the metals of interest and the tracer concentration. And by doing that, we're able to then calculate the loading, and that's how we determine whether these sources here or these sources here, or sources we can't even see or we don't know about, are causing a significant increase in the pollution. So we did that at Wanlock Head. This is a sampling plan for Wanlock Head. This is approximately 2 kilometers of river course. The village is to the southeast here, and the river flows to the northwest. We have numerous sample locations down here based on the information that we got from the Coal Authority report. Some of them are land-based features. For example, this area here is an area of capped tailings. We've got a crushing mill. We've got a tailings ponds area here where they settled out the fines and tried to recover more lead from those fines. And then we've got the smelter mill at the bottom end here. And what happened historically is the mines were up on both sides of the valleys here, and the ore was transported down through the valley on small trains to the crushing mill, and then on to the tailings ponds and into the smelter mill. So you've got loads of different sources. And then on top of that, we have mine water discharges coming in from the right and the left and various different locations down the river. So this was a big exercise for SEPA. We decided to do this in-house with our staff and our labs in partnership with Patrick Barron at John Moores University and he helped us prepare papers and also obviously got some research out of it. So everyone benefited. And you can see us here on site. Not as glamorous as it might appear. IBC full of water from the river, so we weren't changing the concentrations using the tracer. And then full of salt, diluted salt. It took quite a long time to dilute all the salt that we needed in here. We ensured that the tracer wasn't too high a concentration, so we spoke a lot with our ecologists and our chemists before we did the work to make sure that what we were doing was compliant, because it wouldn't look great if we weren't. And then literally we have a tent with a electric battery powered pump that was built by some of the engineers at the university, and that pumped the tracer into the river at a very steady flow rate. And then once we had that stable graph, we brought all our lab staff to site, and we had a filtering tent and a collection process, and it was done in a day. I think we did about 40 samples in the day, got them off to our lab. So some of the results, we've got here a graph showing stream flow and the tracer concentrations. As you can see, as you might expect, the tracer concentration reduces as the flow increases. But what you can also see is you get a very good idea of where flows are increasing. So for example, where we've got the dotted lines here, these are water inflows, either burns or mine adits. And then the shaded areas are areas of significant land features that we were interested in. Really interesting to see little increases around here where there was no stream flow, but quite a lot of mine waste to the side. And then also you can really see the impacts of the mine water discharges here and at the start as well. The lead is the most interesting thing, the way it behaves. So lead's coming mainly from the land-based sources. So you can see the increase here, which is actually a wetland area where there's obviously deposition and remobilisation occurring. And also this area here, which is known as tailings ponds, Queensbury tailing ponds, that is a large area of uncapped mine waste. It was the photograph at the start of the presentation. But what you also see is the lead drops off afterwards, and we really see lead behaving differently to cadmium and zinc. It is largely in particulate form, even where it's dissolved in this graph here, it's largely, we think, in particulate form. So although it's passing the 0.45 micron, it is sinking out of the watercourse, probably largely through flow transport mechanisms. And so the cumulative level of lead in the river continues to rise, but the actual level in the stream flow, there's a 50% reduction in the dissolved fraction and a 72% reduction in the total samples. So it really tells us it's important that mobilization is a key thing here, a key issue, and it's from land-based sources. Just to compare that to cadmium and zinc, you can see very steep increases from the mine discharges and smaller increases from the land-based features. It's still a source, but it's an issue. And I can demonstrate this. I'm going to have to watch my time, so I'll flick through a few of this, but I'll demonstrate this by some of the photos. That's the first photo is the Bay mine adit. It's largely cadmium and zinc. It's crystal clear. This is an area of capped mine waste. Doesn't really cause a problem. This, however, causes a significant problem. This is the tailings ponds in a flood event, and it's pretty obvious what's going on here. But this is occurring in all states of flow. And we see that from some follow-up work we did with with salt gauging and low flow. So you've got the lead sources on the right here in high flow, and then similar thing in low flow, but interestingly more out of the mines themselves. So I'm aware I'm running out of time, so I'm going to skip through my last few slides. Final couple of slides, little heat map here of the lead concentrations on that mine waste, up to 6%, 60,000 milligrams per kilogram in certain places. So it's really high, and it's a real issue. And then again, just to zoom in on the increase of lead from that source at the tailings ponds, you can see in the river it's going from, in dissolved sense, around about 100 to up above nearly 400 micrograms per litre. So it's a big issue, and it's really why we're working with all these partners to try and remediate this under our restoration project. These are the aims of the restoration project. It's a massive project. We're focusing on the tailings ponds initially, and then our intention is to go wider into the catchment and try and come up with some solutions for the other areas of other sources of pollution. And without being any later, I'll close it at that. Thank you very much.
You managed to pull it right back on time with my rude interruption there, Alan.
No, but, I could prattle on about this for hours.
No, that was excellent. And I can't say I said your site setup wasn't glamorous with that backdrop. I think that was actually quite glamorous, actually, to have that in the background. But yeah, you're perhaps a bit more used to it than I am. Yeah, thanks, Alan. So we'll join the team for Q&As shortly. Thank you. We now have another first-time organisation presenting to us today. So I'll say Crowy So to Natural Resources Wales and Louise Siddorn. Louise is a lead specialist advisor for abandoned mines at Natural Resources Wales, NRW, working within the Wales Metal Mines programme. Louise specialises in the legacy impacts of historical metal mining and the challenges posed by metal contamination in the environment. This includes defining the scale and nature of metal pollution from abandoned mine sites, developing robust conceptual site models, and supporting the planning and delivery of intervention work to reduce pollution. Prior to joining NRW 6 years ago, Louise had 16 years experience as a contaminated land officer and formerly an environmental consultant. Louise's presentation is titled Wales Metal Mine Programme, Abandoned Lead Mines. So I'll pass over to you, Louise.
Thank you very much. So I'm going to talk about the Wales MetaMine programme. There some bits that might be duplicating Alan's, but hopefully it will complement what Alan had to say. So in NRW, we started looking at metamines in earnest in 2002 with the Wales MetaMine strategy, but it wasn't until 2020 when we had some funding from Welsh Government and we set up the Wales MetaMine programme as a joint programme with the Mining Remediation Authority, was the Coal Authority, with the aim to reduce pollution from the abandoned metamines. So this is just a quick slide showing the minerals we get in Wales. So in the central kind of ore belt, in Ceredigion and Paris mainly, we've got lead and zinc and silver mines, a bit of gold and Snowdonia, some more lead and zinc at the Gwydir Forest and Halkin Mountain, and Paris Mountain copper mine, which is a very pretty picture of. So we started our work, we commissioned the Coal Authority, as was, to do a report called the Failing Water Bodies Report. So we'd identified there's 1,300 mines, which is the picture on the left, the dark blue. And so we looked at where there was an impact on the water body, so where they were failing the Failing Water Directive. And then as part of that work, the study identified that there was 129 red sites where there was clear evidence that the mines were contributing to the failure of the Water Framework Directive, and 140 sites which were amber, which we were unsure about, wasn't enough evidence to say they were or they weren't. So following on from that, this bit of duplication of Alan's, sorry, but it's just a conceptual model of where we get the pollution from the abandoned mines. Some of it is from erosion from the spoil directly into the watercourses. Others is from leaching through the spoil and the diffuse pollution, or from the adits or the drainage levels themselves. When the mines were operational, it was key to control where the water was coming from. There would be reservoirs above the mines, there'd be leach systems to use the water in processing, but also they didn't want the water in the mines, so there'd be pumping and drainage levels. So the drainage levels is where the lowest point where the water comes out, but a lot of the time there is flooded workings below that level. Just a bit of sciencey equations for some of the chemists out there. The main problem with the abandoned mines is now there's oxygen in the mines when there wasn't before we drilled a load of holes in the hillsides. So it's just demonstrating how we get the hydroxides and sulfides with the metals that come out. So to help us understand the mines, we undertake water quality and flow monitoring. So this is a mixture of staff going out and actually doing the samples on the left. We've installed some flow monitoring structures, so where we can record the flows every 15 minutes. So this gives us a much better understanding of how quickly the water comes through the system. We know we get peaks, but if we're only monitoring once a month, we won't find those. So we can see if the water flows increase and how long they're elevated for after rain events. And then it's not just about the water quality and the flows, it's also about the ecology, so some kick sampling picture of there. This is a look at the Ystwyth catchment, which is in Ceredigion. There are a lot of metal mines on it, and it was looking at the Water Framework Directive, where the rivers fail and what they fail for, as like a starting point to look at where we need to focus our efforts. So you can see the red and amber mines marked there, and also the rivers themselves, the moderate quality or the poor quality rivers. And so then our work at Cymystwyth, we've done lots of monitoring and lots of working out what the main sources are. And Pew's adit in the middle is about 25% of the zinc comes out of Pew's, but the lead levels obviously increase from 63 kilograms a year upstream, and then downstream to 2,400. So it's a significant input into the Ystwyth. And so this is a kind of where the stage we're at with the Ustereth one. So it's at a designing stage. So the aim is to reduce 50% reduction in the metal loadings with 3 broad interventions. So to try and keep the clean water clean, stop it picking up contamination that runs over the spoil, dealing with the contaminated runoff from the adits, and the mining spoil once the water's got contaminated with it along the Ustereth itself, and kind of stabilising the spoil that is right on the river edge so that it doesn't get in. That's kind of like a phase 1, and then we are aware after monitoring we're probably likely to need to do some mine water treatment, so it's included an area of where we might put that. So as well as being in very beautiful parts of the country, there are some big challenges with the metal mines. A lot of them are designated sites. There are triple SIs, there are SACs. We quite often have Calamarian grasslands, so they're metal-rich metaphilitic species that particularly like their metal contamination in a way. The picture on the top left is a site called Gorgulian that is actually downstream of the Ustereth, and it's part of the Commercial Works having to do lots of assessments because that SAC, there is a concern that if we clean up the water at Cymystwyth, then it might have an impact on the SSE downstream, which relies on an input of heavy metals. So some of our solutions, one of the best things we can do is keep the clean water clean and keep it out of the mines and out of contact with the spoil. So the picture on the left is at Frongoch. It's a concrete canvas lined channel to keep the water away from the spoil. The picture in the centre is a half pipe that was installed on a stream above the Cymraidal mine, which before the half pipe was there, all that water in that stream would disappear straight down into the mine and then pick up whatever metals and come out contaminated at the other end. And the one on the right is like slowing the flow upstream of the interventions. So this is just an example of something that has been good and we've achieved. At the Frongoch adit, through surface water management, we were able to divert the stream, stop it going into the stope and the workings, and that led the reduction of the flow from 87 litres a second to 15 litres a second, which has significantly reduced the amount of tonnes of zinc we've got there. I know I should be talking about lead, sorry, I didn't get the lead numbers. And that's just a picture of the flow structure we've put in now and the graphs we get that shows the peaks and what's going on. Another erosion controls, this is more of a temporary solution while we find a more permanent thing. These are tips at Esgamoin. So the lead concentration in the tips is between 0.5 to 18%. So whilst it's a waste, it nearly could be considered an ore. So we've put these baffles in to slow the surface water and capture that mobile sediments, because every time it has a rainstorm, it washes away more into the river catchment. And this is another example of a similar thing at Weems. We put some rock rolls in to shore up the toe of this tip because the stream was running around and eroding it. And then the other side of this tip, near these tree lines, the other stream that comes in was actually undercutting it all. So we've diverted the stream slightly away, built a bank in between, and hopefully that will vegetate and stop that spoiled material ending up in the catchment. This is another leaky dams upstream of the surface water diversion. If we can slow the flow, not have water coming through in such high events, that's all good. And this is Frongoch again, but further away, a bit further up the hill from the adit. So capping and remediation was done. And so there's a before and an after photo, and it reduced pollution of 8 tonnes of metals annually for the stream that was flowing off to the top of the picture. And in 2014, brown trout recorded for the first time ever in that stream. So one is better than none. So we need to talk, if we're talking about solutions, we need to talk about mine water treatment. So these caveat, these aren't in Wales, these are both in England, sorry. So the one on the left is Wheel Jane, which induces lime and uses lots of electricity and creates a metal-rich sludge. So that's an active treatment, so it's very industrial looking. Whereas the one on the right is at Force Crag in the Lake Districts, and it's vertical flow ponds, which use compost to have a bacterial process to get metals into insoluble sulfides. This uses less power, but it does still produce a metal-rich waste, which will need emptying occasionally. So there isn't yet a metal-amine treatment in Wales, but we are working on it and working with various partners, but we've been trialing different things over the years. So on the left, there's a site at Abbey Consols where we've been trying sodium carbonate dosing trial to raise the pH and reduce the zinc. And then on the right was some dispersed alkaline substrate trials that we actually trialed at Paris Mountain, which is pictured there, but also we tried this at Cymraidor as trying to find an alternative solutions, because every mine water is different, the pH is different, the concentration of metals is different, they're complex, some are flashier catchments, some you get more water, different summer winter regimes. It's not as straightforward as you would think. Can't talk to contaminated land officers without talking about Part 2A. So in Wales, there are two sites that have been determined, on metal mine sites that have been determined as Part 2A. So one of them is Pandora in the Gwydir Forest. So it was determined by the council in 2007. It was used by bikes as nice ramps and jumps. So there was a risk, a human health risk. So as part of the remediation, the site was reprofiled and the site secured. So it's now nice and flat, so not so attractive to riding your mountain bike along. The site still, the water quality still is an issue. So we are currently doing some monitoring and looking at options of how to reduce the water interaction with the spoil. But the site is a SSSI and an SAC for the lower plants, which on the photo on the left, you can see there was some trial plots to encourage them to grow and help stabilize the site. And the other contaminated land site is at Henwaith Ponds, which is on Anglesey. It's just to the northeast of Paris Mountain. So as part of a project in 2002, there was a concern of a blowout of contaminated mine water from Paris Mountain mine. And so as part of those works, a choke dam was removed from the bottom of a shaft, which reduced the water levels within the mine. So majority of the water is now flowing to the north of the mine, which meant the water was no longer flowing south to these old precipitation ponds. This led to the ochre ponds, settling ponds drying out. And then there was because of the houses that you can see here, there was an issue of the metal contaminated windblown dust with arsenic and lead in it. So the council got some money as a contaminated land grant, and part of the works was capping, and other parts of the solution was recirculating the water and keeping those ponds wet. But that still hasn't addressed the water issue. This is another lead mine, park lead mines in the Gwydir Forest. So this one I've included because it was remediated in the late 70s and early 80s, like quite a few of the sites in Wales. They were remediated from human health and visual reasons. At Park, they were concerned they had a storm event that washed a lot of spoil out into the floodplain. So they realised they needed to do something about it. So the photo in the bottom, you can see that was the big tip that was left there. A lot of these sites, they haven't particularly been looked after, and the water issue is still there. So we tend to find that it's just concentrated the outputs from the tips, such as that lovely orange colour coming out. Another issue we have with on the Metal Mines programme is sometimes we have humans interfering with things. So this was a pollution incident on the Liquid near Betzicoid. The river turned orange. It happened to be on a couple of Saturdays it happened, and when we went and had a look, you could see that the stones had been moved out of the bottom of the channel to lower the water level, and there was ochre on a top of a barbed wire fence. So it was very suspicious that someone had been in there. Hopefully this plays. So this is a blowout that happened at Cumridle in 2016 on the Adit 9. So there was a buildup of pressure behind the buildup of pressure, and then the water came down the hillside. And we've done works recently where we've installed a new adit because the old adit was all in spoil up to right here, and there's rockhead. You can see from the geophysics that was done, there was a collapse, and this bit was where the water should have been flowing out, and so there was a risk that it could happen again. So we've installed a new adit, so we shouldn't get a blowout like that. It doesn't stop the continual contaminated water coming out of the mine, but it just stops a shock event like that happening to the river. Other impacts that you guys might be a bit more interested on is we funded some research into the environment and wildlife and river invertebrates. That led to some of the people involved finding out about some eggs being contaminated from chickens that were pretty much living on some mine spoil. So we worked with Ceredigion. Ceredigion Council did some surveys for the eggs for sale and didn't find a problem, but then it's just something they are very aware of in their area. And the other thing is we're in the press a bit at the moment. It's dealing with those communications and having an input where we can. And one last thing about climate change. So in 2025, we had a wildfire at Cumridle, so that melted some of the plastic pipes you can see on that blowout video. And so they've had to be fixed. And then also a news article, it was linked to Cornwall, but the storms are triggering mine shaft collapses there. These mines are over 100 years old. The wood is going to rot. Things are going to happen in the mines that we can't control. And it's just something else to consider. And that's me. Thank you very much for listening.
Excellent. Thanks, Louise. A lot going on, I suppose, safe to say. Yeah. Wow. So we're now going to have our second Q&A session with bring back Robert and Alan as well as Louise. So I'll pass over to Phil.
Hello again, everybody. Thanks for another set of fascinating presentations. I've had some questions submitted. Hopefully you had a little bit of pre-thought on them. You may have seen them. First of all, Robert, on your presentation, question about cost, and is it cost that we don't tend to see much bioaccessibility tests in planning sites? Do you think that will be useful?
Yeah, no, I think really bioaccessibility, it does vary significantly across areas. And when you start plugging it into kind of modeling tools, it has a significant kind of impact on criteria, kind of SSACs. So, my view is, it's not always practical from a cost point of view, especially for kind of small sites. But yeah, wherever possible, I think it should be undertaken.
Thanks for that. And just kind of related to that, I think an eagle-eyed person spotted that the bioaccessible fraction in the original data seemed to be higher at some locations than the measured soil concentrations. or did they misread it?
I mean, I think the original kind of lead concentrations were all, and as I said, I mean, we did have some kind of high concentrations, 38 kind of plus thousand, quite a few around kind of 8,000, 9,000. So we tried to kind of include some higher samples and also some kind of some of the average and lower samples. But yeah, at the end of the day, I mean, it's an estimate, and yeah, we used an average for bioaccessibility. I hope that answers the question.
So if not, they can perhaps pop it in the Q&A. Maybe you can pick it up directly. Quick one about the capping layer. The 400 ml capping layer was recommended. Is there any reason why that specific depth was used?
Yeah, it's a good question. I mean, there's quite a bit that got left out of the presentation to try and kind of squeeze it into 20 minutes. I mean, in terms of the investigation across the site, the soils were quite loose, down to about 0.4 meters, and kind of below that level, there was kind of more like kind of demolition waste, which during the investigation we actually struggled to get deeper than 400 mil. So that was kind of taken into consideration. It's also, I mean, in terms of the remediation, I kind of insisted in kind of because we did have more limited testing at below kind of 0.4 meters, 0.3, 0.4 meters. So I insisted on additional kind of verification of the formation level before any clean soils were put in place. The other thing with the site is that it is a local authority owned managed area. And so, I mean, generally there's not going to be people growing vegetables at ground level. And I mean, the council also kind of provides raised planters as well for that area. Right. So, yeah.
The kind of site specific, yeah.
Yeah, exactly, yeah.
Are you finding consultants are now using your K4 SIs, and any evidence of their misuse yet?
Not yet. I mean, obviously I've been pushing it with consultants over the last year, and yeah, I mean, so people have used the principles and they seem to kind of embrace it well. I haven't seen any misuse yet, but I think there will be at some point. just from experience.
Thanks, Robert. Moving on to yourself, Alan. Great presentation, really interesting. There seems to be some interest in your fish.
Always interest in the fish.
Has there been any effect on salmon? And also a question or a thought about the black tails with lead replacing iron in the blood. Could that be poor circulation? Any info on that you might have?
Okay, so a couple of things there. So in terms of the fish that we found it in, the pictures I showed were from an electrofishing survey that SEPA undertook to help our classification, and we only identified it in trout, with the exception of one fish. However, we're the restoration project that I talked about that I didn't really talk about enough, to be honest, but ran out of time. One of the partners is the Nith District Salmons Fishery Board, and they obviously do themselves regular electrofishing, and they find it in both salmon and trout, in the Wanlock, and to a certain extent in the Croik as well, further downstream. Remind me of the other question, Phil.
lead replacing iron in blood, could that be the cause of the blacktails? Could poor circulation be the
It
cause
could
of?
be. There's quite a lot of research from there's a bit of research done on this in the States in the 70s and 80s, and there's various mechanisms suggested as to what's causing it. It absolutely could be, and I'm not going to sit here and tell you I know the answer though, because unfortunately I'm not a fish ecologist. I'm not a biologist, but but I think one of the things that's important for us going forward is to better understand that, because, and it's one of the key objectives of our project, is to work with the Salmon Fisheries Board, and there you tap into their links with academia and other specialists in that area, and potentially, I mean, there may be crossovers with human health, the mechanisms of all this, but and really to understand that better, because what we want to do is try and improve the situation, and if we can understand the mechanisms and help that to target our remediation solutions, then that's something that we really want to explore and find out a bit more about. You know, there's some of the research that's done in the past that identifies other impacts as well, such as spinal curvature. We did see some of that in some of our sampling, and it seems to be about prolonged exposure to lead. So it probably links back to what the way Sarah was talking about previously. It's about the dose and how long the dose lasts and how that happens in the juvenile fish as they grow. But I think the thing that's confusing our fish ecologists and the Salmon Fisheries Board is that we see some fish with it and we see some fish without it, but they're resident populations. So why is that? That's how we want to try and take this forward. It's not a quick fix, but it's something that we hope will deliver. And, you know, I talked about the project having multiple benefits. We hope it's something that will deliver more knowledge and understanding of this issue.
Okay, thanks for that. Another question. With the fish with you might have touched on this, so if I've missed it, forgive me. The fish found in the Wanlock water or downstream, and are you finding obvious impacts further down, such as in the Neath? And this may be somebody with local knowledge, I suspect.
Short answer is no, we're not finding impacts in the Neath. Our SEPA survey went all the way down the catchments. We found the black-tailed fish to a little bit beyond the confluence with the Croik. The same with the diatoms as well. We've seen these mutated diatoms, and we've seen that impact to a similar extent. We did a sort of a clean sample in an opposite catchment away from the lead mining area, and we didn't find those impacts, but we did find some fish that had perhaps gone upstream into that river at the very bottom of it. So yes, we do see impacts beyond the Wanlock, but not far, and certainly not to the Neath.
Okay, thanks. And one last one for yourself before I get around to yourself, Louise. Were any actions taken to identify private water supplies that might have been at risk?
Yes, I believe this was done as part of the public health investigation that was done probably 15 years ago now. I think somebody put a link to it, to the output from that in the chat. I think it was yourself. Was it yourself?
Okay.
Someone put a link in there.
Okay,
yes.
Sorry. Yeah, that's that link that Kirsty put in.
Yes, they looked at that. There were private water supplies in Wanlock Head. People were taking water out of the river. There is now a separate water treatment system and supply for the village, for both villages actually, that's pumped in from a separate catchment. And we also check downstream as well. So there shouldn't, as far as we're aware, there's not any private water supplies coming out of the river or the groundwater.
Okay, great stuff. Thanks for that. I'll perhaps take some more questions into the panel later. Louise, again, thanks for your presentation. How was that funded? Somebody put it looked expensive. Was it?
Which
All
bit?
relative, of course.
Yeah. So we're funded from Welsh Government. So we're a joint programme with the Mining Remediation Authority, but Welsh Government provide the funding as part of their Nature and Capital Emergency Fund. That's how we get our money.
Okay, and was it expensive? I mean, in the scheme of things, I mean.
So some of those, some of the interventions were cheaper than others. So the rock rolls and the baffles, they don't come that expensive. But yes, the tunnelling and forming a second adit, that was expensive.
Yeah, big bucks. And what continuous monitoring are you doing on the sites?
So at the moment, it's just the flow monitoring on some of the main sites we're looking at to get that better understanding of the flow coming out. The technology isn't there to monitor continuously for metals. So something we'd like to do, but it's not something we are able to at the moment.
Yeah, okay. Okay, thanks for that.